Hello everyone. Today, we're diving into the exciting world of machine learning fundamentals, a cornerstone of artificial intelligence. Our goal is to understand how machines learn from data, allowing them to make predictions and decisions autonomously. First up, let's explore supervised learning, a fundamental paradigm where models learn from existing examples. In supervised learning, we teach machines using labeled data, meaning each input has a corresponding known output. One major category within supervised learning is classification, which helps us sort data into distinct groups. Classification models predict discrete labels or categories, giving us clear, separate outcomes. For instance, classifying an email as either spam or not spam is a classic example of a classification task. The primary goal here is to accurately map our inputs to these specific, predefined output classes. Another crucial type of supervised learning is regression, which focuses on predicting numerical values. Regression models are designed to predict continuous numeric values, allowing for a range of possible outputs. An excellent example is predicting house prices based on various features like size, location, and number of rooms. The main objective of regression is to model and understand the relationships between different variables. Now, let's look at some key classification algorithms, the tools we use to predict those discrete categories. These methods are essential for predicting discrete categories, helping machines make informed decisions. Logistic regression, for example, is a powerful algorithm that models the probability of a binary outcome. Decision trees work by splitting data into subsets based on features, making predictions through a tree-like structure. Support vector machines, or SVM, aim to find the optimal hyperplane that best separates different classes in the data. Finally, k-nearest neighbors, or KNN, classifies new data points based on the majority class of their k-closest neighbors. Next, we'll explore some core supervised learning formulae, which are the mathematical backbone of these predictive models. These formulae represent the mathematical foundations of predictive models, driving how machines learn and make predictions. Let's start with linear regression, a foundational model for understanding linear relationships. The formula is y equals beta naught plus beta 1 x plus epsilon, representing a straight line relationship. Here, y stands for the dependent variable, which is the value we are trying to predict. X represents the independent variable, which is the input feature used for prediction. Beta naught and beta 1 are the coefficients of the model, determining the line's intercept and slope. And epsilon signifies the error term, accounting for the unexplained variability in the model. This formula models the linear relationship between variables, assuming a direct, proportional connection. It's specifically designed to predict continuous output values, like house prices or temperatures. The model works by minimizing the sum of squared errors, finding the line that best fits the data points. Now, let's move to logistic regression, which is used for predicting categorical outcomes. The formula is P of y equals 1 given x equals 1 divided by 1 plus e to the power of minus open parenthesis, beta naught plus beta 1x, close parenthesis. Here, P of y equals 1 given x represents the probability of outcome 1, given our input features. X again denotes the input features, which are the variables we use to make our predictions. Beta naught and beta 1 are the model coefficients, which influence the shape of the logistic curve. This formula models the probability of a binary outcome, like yes or no, or spam or not spam. It uses the logistic function to transform the output into a probability, ranging between 0 and 1. Logistic regression is commonly used for classification tasks due to its ability to predict probabilities for categories. Let's explore unsupervised learning, a fascinating area where machines learn without explicit guidance. This method focuses on discovering hidden patterns and structures within data that has no predefined labels. First, we have clustering, a technique used to group similar data points together based on their inherent characteristics. Clustering essentially groups data points that share common features or properties into distinct clusters. It helps us identify natural groupings or segments that exist organically within our dataset. Next, we delve into dimensionality reduction, a crucial technique for simplifying complex datasets. This process aims to reduce the total number of features or variables in your dataset significantly. Importantly, it preserves the essential information while simplifying the data for easier analysis and visualization. Now, let's break down the k-means clustering process step by step to understand how it works. This is an iterative process where data points are repeatedly grouped until optimal clusters are formed. The first step is to choose K, which represents the desired number of clusters you want to find. Next, we randomly initialize K centroids, which are the initial centers for each of our clusters. Then, each data point is assigned to the nearest centroid, forming preliminary clusters around them. After assignment, we update each centroid's position by calculating the mean of all points assigned to it. We repeat these assignment and update steps until the centroids no longer move significantly, indicating convergence. Let's explore the reinforcement learning framework, a powerful paradigm for training intelligent agents. Here, an agent learns optimal actions by interacting directly with its environment and observing the outcomes. The agent is the decision maker, the entity that performs actions and learns from its experiences. An action is a move or decision made by the agent within its current environment. The state describes the current situation or configuration of the environment at any given moment. The environment is the world where the agent operates, providing states and responding to actions. A reward is a feedback signal from the environment, indicating how good or bad an action was. The policy is the agent's strategy, defining how it chooses actions based on the current state. Now, let's dive into key model evaluation metrics, essential tools for assessing machine learning performance. These metrics help us accurately measure how well our models are performing across various machine learning tasks. Accuracy tells us the proportion of all predictions that were correct, giving an overall performance measure. Precision is the ratio of true positives to all positive predictions, showing how many identified positives are actually positive. Recall is the ratio of true positives to all actual positives, indicating how many actual positives were correctly identified. The F1 score is the harmonic mean of precision and recall, providing a balanced measure of performance. MAE, or mean absolute error, calculates the average absolute difference between predicted and actual values. MSE, or mean squared error, computes the average squared difference between predicted and actual values. R-squared represents the proportion of the variance in the dependent variable that your model explains. All right, class, let's quickly summarize the key concepts we've covered in our journey through machine learning fundamentals. Here are the most important takeaways from our exploration of machine learning fundamentals that you should remember. First, remember that supervised learning utilizes labeled data to perform tasks like classification and regression accurately. Next, unsupervised learning excels at finding hidden patterns in unlabeled data through methods such as clustering and dimensionality reduction. Then, we discussed reinforcement learning, where agents learn optimal actions by interacting with an environment and receiving rewards. Furthermore, understanding model evaluation metrics is crucial for assessing performance and selecting the most optimal machine learning models. We also explored key algorithms like logistic regression for classification, k-means for clustering, and Q-learning for reinforcement learning. Finally, proper model selection is vital to prevent common issues such as overfitting and underfitting in your machine learning projects.